There is an infinite number of correct solutions to this problem. There's an infinite number of correct solutions because I gave you no rules, right? No limits, conditions. I just said I want to know the three types of discontinuities. And if you draw a function, I probably should have said that I want it continuous everywhere else, okay? But let's start with the removable at 5. 1, 2, 3, 4, 5, 6. Boom. There's a removable at 5. And I don't care where you put the hole, and the point, and the line up and down. I don't care about the angle of this line. All right. The next thing up is infinite at 3, which means I'll put in an asymptote at 3. Should I go to positive infinity or negative infinity? It doesn't matter, does it? Should I go to positive? Let's realize I could go here. Or I can go here. Right? Or how about we do both?
Wait, you don't go through the solid one?
No, because I need a limit. But if it's a removable, that's not a jump. That'll be the jump. It's not a jump. This is removable. So, again, I'll get rid of all this. So I will just finish it this way. And everybody, right now, the limit as x approaches 3 right now is positive infinity, right? Because both the left hand and the right hand would be the same.
Yeah, I just go like that.
Well, if you didn't multiple graphs, that's fine. I would say one graph. So on 1, I said make a jump. I don't care if you put it open here or a solid here, and I don't care if you put it open here or a solid here. But here's what I want. I want one of them filled in and then a jump, right? And if you filled in that one, leave the other one open. If you fill in this one, leave the other one jump open. And what I want you to witness, if I put an arrow on this one over here, do you guys agree that this graph is continuous everywhere but 1, 3, and 5, the way I've drawn it? It is continuous everywhere. So if I take a limit anywhere on this graph, I say limit as x approaches a of this function f of x, and an a cannot be 1, 3, or 5, all right? I think we should be able to fill in this blank. A little more particular. It is real, but a little bit better answer than that even. I think we actually know the value of this. What if I put a here? What's this y value called?
F of A.
F of A. So I think this is f of A, because if I move this and I use yellow, do we care if A is here? No. What's this value? F of A. What if I go here?
Wait, so if it's a
F of A.
polynomial, does that mean it's true?
This is obviously not a polynomial. You agree? This is obviously not a polynomial. Here's what I'll say. If you know the function is continuous, you know that this relationship is true. And the function we drew on the board was continuous everywhere but those 3 numbers.
So for all your like other functions that like continuous everywhere,
So when you start talking about your mother functions, we know that this is true for all polynomials everywhere, lines, power functions, root functions in their domain, right? Rational functions in their domain, trig functions in their domain. Now, parabolas are polynomial, right?
Oh, right, yeah.
So all those, all right? Again, calculus is fun. That's why it starts with F. There.